Life is big, messy, and extremely complicated. It's also continuous, a complete spectrum of variation across everything that is living on Earth today. So given that, how do we make sense of it? How do we break down that variety into bite-sized chunks that we can talk about sensibly and actually understand what we mean? It turns out we're using two different systems at the same time, and at the moment it seems to be working, even if nothing is quite perfect. Firstly, I just want to thank everyone who has joined in with this channel, subscribed, made comments, liked videos, or just enjoyed the content, because I'm actually amazed by how quickly this is picking up. I've been doing this for about a month and it's looking good. So thank you everyone for joining in. And yeah, I'm going to carry on. So special thanks on this one to the wonderfully named Lala Custard, who would like a video on how we do taxonomy. So here it is. Thank you. Taxonomy is the basis of biology in some ways, in that it is the way that we break down the diversity of life into units that we can talk about, whether that's species, phyla, kingdoms, and so on. It's how we can understand the range of life that there is out there and keep track of it. However, first thing to note is that life itself is not broken down in that way. It's an entirely artificial system. Life itself is a spectrum, one thing blending into another through evolutionary processes over long periods of time. So ultimately everything's continuous, but we are artificially breaking it down into blocks that we can talk about. The second thing is that the system that has been used traditionally, and still is to a very large extent, is Linnaean classification. And this was created before we knew about evolution, which leads to its own problems. And that is why we now have two systems working at the same time. Let's start with species. A species is the common basis that both of these systems use, and it is defined as an interbreeding population that can reproduce to produce fertile offspring. That last part is important because, for example, horses and donkeys can interbreed to produce a mule, which itself is not fertile, and therefore horses and donkeys count as separate species. So this is just an example. There are lots of similar cases. There are also lots of exceptions when you get into the details. So the bdelloid rotivores, for example, are entirely parthenogenetic. They are, as far as we know, entirely female and have been for about 40 million years, I think it is, and therefore they don't interbreed at all. But, you know, life is messy, as I said, and we can not worry too much about the exceptions. We know what we mean by a species. A species is named based on its morphology, effectively its form, including all of the details, all of the features that allow us to recognise it, separate from everything else. It's now coming into play more that genetics is having a role in defining them, because there are some things we can't separate without genetics. And yeah, there is actually a big book of rules as to how you go about naming a species. So this is the International Code of Zoological Nomenclature. It's quite an old version now. This is only the 4th edition. Since then we've had the internet. This was 1999, which has completely changed things, and it is now much bigger. A group of related species are lumped together into a genus, plural genera. This is rather arbitrary in that a genus represents a different level of variation from one group to another because of historical traditions and just which groups are better studied. Basically, the more we study a group, the smaller the genera tend to get and the more of them. So a genus is not the same in two different groups. It's arbitrary. It's completely subjective. The result is that we have, when we refer to a species, a genus name and a species name. So in this lovely case here, it's a plant bug of the species Flavoquadramaculata in the genus Dryophyllocores. Both are always written in italics, with the genus capitalised and the species not. This is just how we do things. So if you see that written without italics, it's not right. Why did I pick this one? Well, it scans nicely for a start. And in fact, you can read Dryophilocores flavoquadranculatus exactly as if it was in Mary Poppins, which it really should have been, I think. Anyway, I digress. The system of genera and species was created by Linnaeus back in the 18th century. What he wanted to do was categorise and describe God's creation. So he didn't stop at genera. Related genera were grouped into families, families into orders, orders into classes, and classes into phyla. Phyla, singular phylum, are the fundamental groupings of animals. So they're defined on the basis of really critical differences in how the body plans are put together. For example, insects like Dryophilocores flavoquadranculatus are placed ultimately within the arthropoda, the arthropods, defined on the basis of jointed limbs and a crunchy exoskeleton. Humans, on the other hand, are chordates. The phylum is defined by a set of characters including a stiffening rod called the notochord that protects the dorsal nerve cord. This was then reinforced into a backbone in most groups. You get the idea. These are fundamentally different groups of animals. Other examples are mollusks, nematodes, sponges and arrowworms. There are about 30 animal phyla recognised today, and probably a few extinct ones that we might come back to later. Above that level, the phyla are grouped into a kingdom, in this case Animalia. There are other kingdoms, and there are even higher levels in the hierarchy, so animals fall within the eukarya, which contain complex cells with a membrane-bound nucleus and organelles. But today, let's just stick with animals. So we still use Linnaean taxonomy now, but it's important to appreciate that this was constructed before we knew about evolution, before we knew how truly connected life actually is. And this leads to a little bit of a philosophical problem. So if we trace two branches of life back through time, and past various branching points where things are diverged, these branches are of course getting closer and closer to each other, because eventually they all go back to one point. But in this Linnaean classification system, as you go further back, they don't get any closer. They stay completely distinct through the entire history. So what happens with Linnaean classification when you actually get back to the point where your branches are fusing together? What happens to your definitions then? The strangest part of this, in some ways, is that it works so well so far back. Even back to the Ordovician, pretty much anything that you find is likely to fit into the diagnoses, the definitions of a modern phylum. And without any squeezing or shoehorning necessary, you can recognise them. And yes, there are a few oddball exceptions, and I'm sure that Mr. Tully Monster would beg to differ, but we're not worrying too much about that today. But still, it works in general back to the Ordovician and even mostly into the Cambrian. The Cambrian is where things start getting a little bit weirder though. For anyone who's not familiar with the term, the Cambrian is the first time that we see the diversity of animal life, recognisable animal life, appearing in the fossil record. There are many fossils in the Precambrian. Some of them are almost certainly animals, others much more debatable, but they're only really in the last part. So animals must have appeared and diversified just before the Cambrian, but in the Cambrian they are really there in the fossil record. We can see them and describe them. In the Cambrian we also have an extraordinary array of remarkable fossil faunas, mostly the Burgess Shale type faunas, which preserve the most exquisite fossils of soft-bodied animals that give us an unprecedented window, for any time period really, into what life was doing at this time. It's there that you start to meet things like the opabiniids, the halkyariids, dynamiscids, all these weird wonders, as they've been called, which Stephen Jay Gould, amongst others, has argued in the past that they were extinct phyla, numerous dead-end branches on the level of a modern phylum, which just failed, fizzled, and went extinct. That's more or less the conclusion you have to come to when you're thinking in Linnaean terms of these fixed categories and fundamental divisions of phyla which have strict definitions. And if you find things that do not fit into those definitions, what do you do except name another phylum? It's all you can do with that classification system. Over the past 30 or 40 years, though, we've got a much better understanding being reached of what these fossils are telling us. These creatures were not completely distinct phyla. They were just little branches from the ancestors of the phyla that we know and love today. These creatures don't fit into modern phyla because they were still in their formative stages. They hadn't yet evolved all of the characters that we use to define them today. These are what we call stem groups, members of a group that evolved before any of the living ones did, and which are therefore a little different. Even better than that, though, we have fossils or creatures that seem to fit between the living phyla, ones that have characters link two or more of these major branches of animal life with each other. For example, Halkieria is now believed by most researchers to be a stem group mollusk, probably alongside the other halwaxiids, which are a complex of armoured slug-like animals of various kinds. However, the wider group includes lesser-known creatures like the tomotiid Wufongella, which shows features indicating a close relationship with brachiopods and phoronid worms, two other phyla. This reinforces the view that the shells in Halkieria might actually be the same structures as the shells of brachiopods, even though the animal itself was likely a stem group mollusk. The exact placement of most of these creatures is still uncertain, but that's the point. Linnaean taxonomy breaks down when you have features diagnostic of more than one phylum in the same animal, and an evolutionary position that's somewhere between them. Enter the Phylocode. This is the second method of classification that is currently being used. It uses thing, species and genera concept as Linnaean system, but above that, in the hierarchy, it changes radically. So rather than having a strict series of ranks like orders and classes, with those levels defined by diagnostic features, morphology, any larger groups are defined instead by their place in the evolutionary tree. It works like this. If you want to define a group, you define it in terms of what it includes. For example, if we assume that sponges are the earliest branching phylum of animals, then we can define the animals, formerly the metazoa, as the last common ancestor of a sponge with any other animal and all its descendants. This generates a large trunk of the evolutionary tree that encompasses all living animals. If we want to define a slightly more restricted group that includes everything but sponges, such as the epitheliozoa, that is, animals with a true epithelium, then we can define that as the last common ancestor of a member of the next oldest group, probably a ctenophore, and something entirely different like Dryophyllocopus flavoquadramaculators and all its descendants. The system does allow some slight variations on this, but ultimately it all leads back to the same point, that you are defining a node, a point in the tree, and all its descendants as being one group. And there are unlimited number of nested hierarchical terms within this, so you can have hundreds or thousands of terms representing slightly more and more inclusive groups as you go down through the evolutionary tree. And this completely gets around the problem of stem groups. You find a new fossil that fits between two living branches, and you want to recognise that branching point? Perfect. You define a new level in the evolution that is based on when that split off from its relatives. No problem at all. The only issue is deciding which part of the tree you're going to interpret your creature as belonging to. We also don't have to find ways to define a group on morphological grounds, which can be difficult. For example, if you look at modern demosponges, they are an absolute taxonomic nightmare, which are only now being sorted out by genetics, because it turns out that you can't identify groups within them based on the morphology alone. They're just too chaotic. So phylogenetic nomenclature, the Phylocode, definitely has a lot of answers to some of these fundamental problems that we see with Linnaean taxonomy. And that's great. It also, of course, has its own drawbacks. So one issue is stability. So in order to have any stability in a taxonomic system, you need sort of sets of rules like this. And then you need names to be fixed once they have been introduced. If, for example, you define one of your clades as being the last common ancestor of a ctenophore with something else, and then we discover that ctenophores are actually the earliest branching group of animals rather than after sponges, then suddenly this clade that you have fixed contains sponges, which it was never intended to. As our understanding of the evolution of a group evolves, it can change radically what is included within a particular group. And that instability can be annoying, but it's just a downside of a system that is based on the evolutionary history. What we have then are two classification systems that are being used simultaneously, mainly by different groups of people. And that's absolutely fine. They do fit together. So, for example, the dinosaur specialists are using almost exclusively now the Phylocode system. And then also it tends to be very widely used in the Cambrian faunas, these stem group organisms where you are dealing with one of the main shortfalls of the Linnaean system. You're dealing with all these things that are somewhere between different phyla. There are also other people, particularly those in more traditional areas where you're dealing with families and orders and so on in a long-established taxonomic system, who are using Linnaean system absolutely fine and never touch the Phylocode. And they don't need to, because that system is still equally valid. So it might seem confusing to have two different types of taxonomy on the go at the same time. But as long as we're clear about which one is being used in which case, it doesn't actually matter. We're both different approaches that have different strengths for describing different parts of the history of life. Well, that escalated quickly. It was meant to be a simple introduction to taxonomy, how it works, and what the differences and the different levels really mean. And yeah, it sort of was that, but it turns out that, like everything in biology and paleontology, nothing is quite as simple as one might hope. If you think it's unwieldy, then you're right. But this is a problem when we are taking something which is entirely natural and a total continuum, and we are trying to artificially break it down into things just so we can name it, to be able to talk about it. It's inevitable that we're going to get something that doesn't really address the sheer beauty of the range of variation that is out there, because it can't possibly encapsulate that. Because that's not what we're doing. We're creating a tool that allows us to talk about things. And talk about things we shall. I already have a long list of suggestions for videos, and thank you very much for those. I also have ideas of my own, of course, and there's a few things that are ongoing. So there'll be, yeah, more of the same. I'm hoping to cover a wide range of topics in biology, natural history, and especially paleontology, and also the links between how they all fit together. So please do stick around, and I will hopefully see you next time. Dryophilocores flavoquadrimaculatum.